Hi, everybody. I'm Tonio Buonassisi. It's a pleasure to be here today. I'm sorry I couldn't be there in person, but I unfortunately did not receive travel authorization given the current environment. But it's a pleasure to present to you regardless on behalf of the ADDEPT team, the great work that's been going on within the ADDEPT Center. ADDEPT is a US national center. ADDEPT stands for Accelerated Co-Design of Durable, Reproducible, and Efficient Perovskite Tandems. It started in the second half of 2023 and involves the following partners. On the industry side, Cubic, Verdi, and First Solar as a collaborator. And on the academic side, UCSD, Princeton, and MIT. We also have participation of Optagon as part of the Massachusetts Clean Energy Center and some colleagues who are with us from other universities as collaborators, such as Ethan Schwartz from University of Washington. So overall, fantastic team, a lot of great energy on our calls, and very collaborative spirit. Our goal is to demonstrate a perovskite module with transparent back contact of sufficient size, durability, efficiency, and manufacturing uniformity so as to stimulate further manufacturing investment. The way we do it is we involve industry as a participant, not just a passive observer. Industry is engaged. There have been over 150 devices and modules fabbed with our industry partners, notably Cubic, and we've been building and testing hardware and machine learning tools together. Second, there is a big focus on principles of transferability, meaning even though you might be working with a lab scale technology, you are thinking about the large area, high volume manufacturing technology and how the work that you do will translate. More on that in a minute. So there's been a gap between university and industry research in perovskites. Notably, the difficulty in translating innovations from academia into industry. And this is what ADDEPT is really trying to address. In terms of technical foci, industry typically is focused on a PIN baseline architecture. Academia, maybe not as much. PIN is called an inverted architecture. And within ADDEPT, we're focusing on the industry standard, PIN, but with an open mind. I must say that the focus on industry goes all the way back to the conception, the original design of the perovskite silicon tandem. This came about in the Bay Area Photovoltaics Consortium as a collaboration between Mike McGee and my teams. Mike, by the way, leads the Team Up Center, which is the sister center to ADDEPT. This idea was really spawned by recognizing that both perovskites and silicon, from a techno-economic point of view, were what is called a marriage of equals, meaning they're similar in cost so that it makes more sense to combine them rather than sell the cheaper one individually. So aerial cost and spectral performance. We're still working on the stability. That's the big challenge that inhibits us from getting into the field. And what's delightful when I look back at my notes is that the BAPVC really served as this nice convening authority. Their tagline was supporting university research to develop technology industry will use. And that continues to be a mantra that is throughout ADDEPT and Team Up today. I mentioned the principles of transferability. How do we even think about the space of getting tech from the lab into our industry partners? If you consider a process window for a lab scale process, let's call it spin coating, for example, and a scaled up process, let's say slot die coating, for example. These blues here represent the acceptable process spaces where you can get a reasonable device. There are certain recipes that transfer. We're just lucky. The right combination of solvents, precursors, and we get a device that translates from one to the other. Those tend to be more rare, to be honest. It is more often the case that we have an unsuccessful transfer. Something works in a spin coater, but it just does not translate to slot die coating. And there are also cases where something is discovered on the slot die coater and it doesn't back propagate to the spin coater in an academic setting. So this framework, the principles of transferability, was really inspired by repeated questions from Tim Siegler, our program manager at CETO, at the Solar Energy Technology Office within the DOE. During the negotiation phase of the grant, he asked a series of questions about how the proposed work would translate into industry, and that's what gave rise to the creation of this framework. And what's important is that we're not just transiting points from lab to industry, but we're translating improvements. In other words, if we have a baseline and an improvement, we have a vector, and we need to be able to show that that vector or the improvement transfers as well. That is why we've spent a lot of time upgrading our baselines to adopt a PIN industry-compatible baseline throughout ADDEPT. There were 3 university labs that established their PIN baselines, 2 that upgraded them. The enabler, of course, being strong industry support to bring the academic groups up to that level. And there were good questions raised by academic partners that said, well, what would change if we were to change 1 or 2 things? Would it enable NIP to come back? And it turns out that yes, there are reasons, technical reasons, why industry has adopted PIN. But if breakthroughs were to be made on NIP, that would be back on the table. And it's an interesting concept to consider, especially if you look at the photoelectrochemistry of PIN versus NIP. There are some advantages of NIP. Credit to PACT and Laura Schellis for really strong guidance on encapsulation. And it's very clear that we and others need to move in the direction of mini modules as an important next step. It does require dedicated resources, though. And as a last provocative step, a thought for the community, PIN is now the industry default. Should we still be calling it inverted? All depends on your frame of view, right? Second technical focus within ADDEPT is moving from a static device model, which is traditional in inorganic photovoltaics, to a more dynamic device model where the constituent atoms are moving. We, to borrow the tagline from Dunkin', Dunkin' Donuts was founded here in the state of Massachusetts, down in Quincy. We say that perovskites run on redox, and the reason for that is this oxidation reduction reactions that happen within the device, both during operation and also during synthesis, we'll see in a minute, govern the stability and ultimately the financial viability of these devices. So Barry Rand's team has come up with a very nice model recently published in ACS Energy Letters, shown here. The gist of it is that you have hole capture by iodide, I- on the lattice, that results in an interstitial iodine that can move throughout the lattice, depending on its charge state, under field effect as well, under drift, and can move to the surrounding layers, interfaces, and even out of the device if one's not careful reacting with the different layers. The vacancies also behave in a similar way. So there are generation of point defects, annihilation of point defects, and mass transport. Very similar to electrons and holes, but in this case, ions. And the working thesis is that you have to manage these motions of ions within the device and ensure that there is a reversibility under different stress conditions, this cyclical day-night pattern that must be balanced for high stability. These are a few of the reactions that have been identified and documented in recent papers, shown here on the lower left from Barry Rand's team. The reaction in particular between 2 A-site molecular cations, methyl ammonium and formamidinium in row 2, forming a larger molecule here that disrupts the lattice, is bad. And there are ways to inhibit that reaction, either by adding excess iodine, I2, or in the work of David Fenning's team, replacing methyl ammonium with something else that is less likely to form these longer chain molecules. This was work performed outside of the ADDEPT Center, but it is relevant, so I'm presenting it here, showing in the case of methyl ammonium a degradation under accelerated stress test conditions and a high reaction rate, high forward reaction rate here to form this larger product, and other molecules that are inhibiting it, yet still resulting in decent grain structure. My predictions in terms of the photoelectrochemistry portion is that redox will become more prevalent in people's minds as we think about optimizing synthesis and operation. There is much to import from the solid-state battery community. I'm sure we'll be seeing more papers over the next few months highlighting those crossovers. I think we'll all step up our chemistry foundations as a community, and hopefully there'll be stronger discussion sections in the papers. And device simulations will eventually have to incorporate this. It's not just about the electrons and holes. There are already some device simulations that are moving in this direction, which is good. Third, degradation testing. So industry performs, by and large, is performing accelerated stress tests in the lab in order to mimic the degradation that happens in the field and predict how the devices will withstand field conditions. In academia, unfortunately, there's a bit of gamification of accelerated stress testing, which I believe is holding back our community. And so within ADDEPT, we're really focusing on designing low-cost, high-temperature degradation and focusing on certain best practices when reporting DEG test or accelerated stress test results. There's a beautiful, beautiful editorial recently published in ACS Energy Letters by Professor Kamat. I encourage you to read it. But the key point here is that there is a pressure on the community to publish efficient and stable devices. There's almost a formula for accessing the high impact factor journals in this regard. It consists of showing a normalized device efficiency versus time, a stable device, a high efficiency JB curve, and implying that these are one and the same, when often they're not. So this is real data taken from a recent campaign in May from ADDEPT, showing the Pareto front here, or a trade-off between efficiency and stability, and this is very common. A most stable device would be this one right here, and the most efficient device would be that one right there, and they're not the same device in this case. What makes matters even more interesting is that it's not the same light source for both. In the case of the device efficiency, we tend to abide by AM 1.5 spectrum, but in the case of stability, not so. So I'm proposing that as a community, we should be showing absolute efficiency versus time, not normalized efficiency. This will allow the reader to see whether it's the same device being measured under the stability and efficiency measurements, right? Even though, yes, the efficiency will change, especially if you increase the temperature. The degradation tests, we should be aiming to include light sources that mimic AM 1.5 or at least have a UV and blue component, because that is important for the degradation. And ideally, we show the same device twice for the stability and efficiency measurements, or if not, show the Pareto. I think the misalignment between incentives in academia and industry development of perovskite research or perovskite technology has really resulted in this overproduction of high impact factor papers, but a paucity of results that translate into industry. So here I'm, just for purposes of illustrating the point, I plotted the ratio of the gigawatts of global manufacturing and divided it by the number of papers published in science. I'm not trying to single out science by itself. They just have a very nice search engine that allows you to do keyword searches, and I was able to pull the data together pretty quickly and efficiently. But the general principle holds here that there are a number of high impact factor journal articles being produced, but the impact has been rather small. How can you help? Signal that industry impact is valued, both from the hiring and tenure committees at universities, also from journal editors. That would help. Industry, get involved, help shape, guide, and direct academic research. And the second thing we need to focus on is improving the cost so that we can scale up DEG stations. This was a real email that I received from a colleague 2 days ago saying, I'd love to do more stability tests, but I can't right now. I just don't have the number of slots available on my DEG station. And this is because the cost is quite high. It's typically $1,000 per channel. I'm hopeful that we'll see this accelerate, and I'm hopeful because it's identified as a priority among the community. Secondly, we've demonstrated within ADDEPT the ability to produce accelerated stress test equipment at $100 per channel or less, a 10x reduction relative to the status quo. And there are several open source efforts approaching publication stage. The diversity of different open source projects should enable us to tweak parameters during DEG tests that will allow us to elucidate the underlying science of degradation. And there are routes to accelerating the degradation tests themselves using forecasting, using machine learning, and higher temperature measurements. And I do see more and more journal editors evaluating commercialization relevant questions, which is great. And Jenny Chase, her annual tweets on perovskite manufacturing may be having a bit of a tone shift. That is a leading indicator. Weak signal here. And PACT has some mini modules that have been out in the field for more than a year, which is awesome. You also see some companies passing more traditional stability tests, which is awesome. For the interest of time, I'm going to highlight a couple more points and then wrap it up. So industry has some degree of environmental control. In academia, we have the ability to make little boxes around our systems that give us full control of environmental conditions. And I think where this is all headed is a greater appreciation for the role of environmental factors during synthesis and operation of the devices, and better sensing and control of those environmental variables. So this is a tool available at our MIT Nano user facility, funded through ADDEPT, which is a dedicated slot decoder for perovskites with environmental control. We have a number of great team members, especially from Vladimir Bilovich's team, and some outside collaborators from University of Washington also have a FOM at their test center, and Daniel Du from UCSD helping on the machine learning side to really ramp this up and get high efficiency, high stability, and high repeatability off of high throughput or high volume manufacturing technologies. This has environmental control. Key point is you can control certain elements, especially the humidity within synthesis. I would refer you also to a recent paper. This was the Hello World Pascal paper from the UCSD David Fetting team. And there were, under a high suspected solvent vapor pressure environment, larger spreads than under low. Again, implying that control of environmental conditions is key to ensuring repeatable and tight distributions in your fabrication. My predictions here is that growing awareness of redox drives more research into environmental impacts during synthesis and aging. Environmental sensors become ubiquitous on synthesis tools around the world. Automated labs, because of their repeatability, will set the standard for environmental control. And then finally, we'll have a chance of making the same device twice in academia. I also hope that the community shifts to reporting absolute humidity, but maybe I'm too optimistic there. I refer you to this paper here, The Challenge of Making the Same Device Twice in Perovskite Photovoltaics. Criminally undercited, in my opinion, great paper to read. And lastly, the difference between manual processes and automated labs or fully autonomous labs. I think a middle ground is selecting which machine learning and AI and automation to apply. For self-driving laboratories, we have automation, machine learning, the combination of both yielding autonomy. And to give you examples of some of the activities happening around the academic partners, this is a hyperspectral image of a series of samples being measured in their band gaps, image segmentation, and then or RMSE fitting of the band edges after tau plot transformation to extract band gaps. And this is the kind of data that you would obtain in seconds, whereas before using a UV vis measurement with manual band gap fitting would take hours. So this is the speed that is given or afforded to you with some of the high throughput machine learning enabled characterization tools. Pascal at UCSD takes us one step further, where the entire fabrication process and characterization, including spin coating and annealing, is done robotically. And the tightness of the distributions that they're able to achieve in at least the implied VOCs in this case, they fabricated some of the device fab steps by hand, so they increased the spread. But up to the point where the robot was in control, very tight distributions, very repeatable. And the vision here is sample to sample and run to run control in an academic R&D setting enables stronger signal to noise and faster technology improvements. Really exciting was this collaboration between David Fenning and Mariana Bertoni, showing transfer between TeamUp and ADDEPT, or actually ADDEPT to TeamUp, between UCSD and ASU, where optical microscopy, SEM, GWAX, and steady state photoluminescence were all very similar, because a recipe was transferred in codified form between two robots, one in David's lab, one in Mariana's lab. So my predictions are automated tools will increasingly improve reproducibility and speed of R&D as more labs adopt them. I think we'll see our community navigating multivariable parameter spaces and moving beyond A versus B experiments, which is great. When properly applied, I think these tools can reduce frictions, moving from laboratory results into high volume manufacturing. And in the near term, until we have off-the-shelf solutions, trained human capital will be an adoption bottleneck, so collaborations will be essential. Let me finish by providing a bit of vision for where I would hope our legacy is with the uncertainty ahead. Where do I hope that the lasting impact, even of just these 2 years of ADDEPT, will be? Of course, I want to see terrestrial tandems get commercialized. That is the ultimate motivator. But just as important is grounding academic research in real-world relevance. It's connecting academic and industry partners to focus on challenges that really matter and prioritizing impact to advance those technologies, not just the publications. Our best work is still ahead of us. I truly believe that. Going down to the laboratory the other day, as a student in the lab was helping to install an automated powder dispensing system, we chanced upon Jonathan Mailoa's original perovskite silicon tandem devices from 2014 timeframe. These are some of the 2-terminal on the right and 4-terminal on the left subcells, silicon subcells. And that reminded me of another engagement. Just before a DC climate conference in January 2015, there was a blizzard that shut down the Boston Logan Airport. I was unable to take off from Boston to go to DC, even though I'd promised Greg Wilson that I would be there. So I drove 200 miles through a blizzard. It took 6 hours to get from Boston to LaGuardia Airport so I could actually take off and meet them. It was an all-nighter for me. But during that conference, I met Rafi Garabedian from First Solar. It kicked off a really fruitful collaboration with First Solar that has been ongoing for over a decade, or about a decade now. And I just wanted to say that nothing has changed in solar, right? We have always had an uphill battle to get this technology out into the field. It is hard today. It was hard before. There were always challenges in our path, and we've overcome them every single time. So I'm hopeful for the future, even though I think it will involve some adapting relative to the way we've been used to working so far. So thank you for your attention, and I welcome your questions.